Chemists tend to make dirty things. And physicists don't like to study dirty things. They want to study things that are really pristine and well characterized.
Which can fit into their theories.
Yeah, we like spherical cows.
Just on something you mentioned before, that gold particles were frequently used like in antiquity to get plasmon resonances in red color. Is the reason that gold was typically used that it's very easy to work with, so pretty much like it doesn't oxidize, it has natural stability, versus some of these other particles that might not have survived the same type of, like, I don't know how they were preparing the gold particles, milling or something like that, but or how would they get very small gold particles, and why was gold a default? Is it the stability or something else?
Well, yeah, the stability of gold is, it's a noble metal. It's
Mm-hmm.
as opposed to silver, which oxidizes, more easily. But they didn't mill gold. It wasn't like they took gold and made it into little particles. So I was given many years ago a recipe from the alchemists on making lead into gold. And the recipe consists of, taking blood from, I don't know, a snake that just bit something, or a cow or whatever. You mix all these ingredients together, all these normal, natural ingredients together, and along the way, you add a little pinch of gold. But the whole point of the recipe is to adjust the pH and to have uric acid or whatever you need so that you make gold salts. So you dissolve the gold and you have gold salts. And then when you take that solution and you dip the lead in it, you're basically coating the lead with a very, very thin layer of gold from the gold that's in the solution. And then you take it out and it looks gold.
That's fascinating. That is very cool.
Wow.
So it's those kinds of recipes, that they use. Basically, they knew how to make gold salts. And then you just put that in the glass. Then you heat it up, and then the gold reacts and aggregates and forms particles.
Okay, yeah, that's actually fascinating. It's very interesting.
I mean, they didn't realize what they were doing. Obviously,
Yeah.
It was all empirical. But humans are amazing in their innovations that they were able to do in those times without really knowing any physics or chemistry. Completely empirical, and they came up with some very detailed recipes that were reproducible on how to make things, and maybe it took a little longer than what we might do today, but it's kind of, in a way, it's kind of like evolution, right? They try something and something works, and they tweak it around and it works better, and it's very Edisonian.
How did it turn to nanocrystals? So was Louis Bruce the turning point that he is like, all right, I would like to figure out how to make the colloidal nanoparticles.
All right, so let me go back
right
to my story with the National Renewable Laboratories and making fuels. How could you make fuels? Well, you have to capture the sunlight first, right?
Mm-hmm.
Semiconductors are really good at capturing sunlight and creating electrons, excitons, energetic electrons, then can be used not just for electricity, but if you can extract those electrons at the band gap into a solution of molecules, you can do photochemistry. So that was a big push there, understanding electron transfer from semiconductors to molecules in solutions to do photochemistry driven by the sun. And so he was using a new kind of laser at the time called a picosecond laser. Today we buy them for very cheap, but they were newly discovered lasers, right? Newly invented lasers. And he was watching the kinetics of electron transfer from the bulk semiconductor through the surface into the solution, trying to understand how fast that goes, because in a way that those kinetics determine the efficiency of the chemistry, right? But he did a higher signal to noise. It's a surface effect. So if you want higher signal to noise, what do? You make the pieces of semiconductor smaller.
Oh, wow.
So you made them smaller and smaller and smaller, and there were recipes already out there for doing largely from Hanglein's group in Germany, who were really interested also in a kind of photochemistry, but they were creating the chargers using radiation rather than sunlight. So there was a whole field of radiation chemistry using small particles of semiconductors back then, bigger, and that's how he stumbled into it. He was using cadmium sulfide as the semiconductor, and he was making cadmium sulfide from cadmium salts and hydrogen sulfide actually at the time at low temperature, and he was watching the particles. He was watching the color change overnight. He would make a sample, and then the next day, it would be a different color, and it was kind of irreproducible. And he thought, "Oh, what's going on?" But he had access to T electron microscopes, so transmission electron microscopes. So he was able to correlate his observation with what the particles that they were being formed. And at first he thought it was a classical effect. He thought it was just me theory. Me theory is what explains
Agglomeration of particles.
Well, me theory is the interaction of light with microscopic particles. So me theory basically, it has to do with the fact that these particles have a high index of refraction compared to the surrounding. So it explains why, sunset is red, right? Red light doesn't scatter as much as blue light. So he thought that the absorption that he was seeing, which was not structure at all, because the particles were really actually pretty bad. So, he saw this change in the absorption onset of this continuum of absorption with no bumps in it at all, no features. So that, that looked like scattering, right? It looked like a kind of scattering. It didn't have features in it. Very much what you'd see in me scattering. But the particles were too small, so he tried modeling it using me theory, and it just didn't work.
Yeah.
How small were those particles?
They were a few nanometers in size.
Okay, so they were already...
They should have been transparent, basically, in the classical sense.
Well, it was a clear and colored solution, right? Cadmium sulfide actually was very, very bluish or yellowish looking, right? And so he was surrounded at Bell Labs by people who were, deep into quantum wells, so all these physicists studying quantum wells, which was starting to become really interesting for lasing, for telecommunication. And because he was surrounded by all these physicists, he thought, oh, maybe this is a quantum size effect, and then that's how he stumbled into it. And he was interested in how the quantum size effect then would affect the oxidation potential of the semiconductor, again, for the application of photocatalysis. If you have a smaller particle of semiconductor, then the electron has more energy than if it's a bigger particle, and then you can then have a higher potential for oxidizing, or in this case, reducing a molecule in the solution and capturing the sunlight that way. So his first papers talked about all these things, about the absorption, the exciton, but also the ionization potential of the oxidation potential of these small particles, because he was motivated by that application. But very soon the application sort of was no longer the guiding interest. The guiding interest became what I was interested in when I joined his group, and then when I submitted my proposal to MIT was, you have atoms on one end of the spectrum, of the size spectrum, and you've got a big thing of mass, on the other end of the spectrum, the bulk material. The properties of the atoms that make up the bulk material are completely different from the properties of the bulk material, right? So somehow, as you put more and more atoms together, the properties of the bulk begins to emerge. How does that work? What is that process as a function of more and more atoms do you get the bulk material? And that was really the curiosity part of the research. How do you understand the properties of materials as they change from molecular to bulk-like, to the solid state? And that was a guiding principle also for other people in a different field. So there was another field of cluster chemistry or cluster physics, where people were mostly metal clusters, where they were making clusters in molecular beings. These were small clusters of gold or silver or whatever that had 5, 6, 7, 8, 9, 10 atoms, and they were watching the properties of these clusters change one atom at a time. You start with one atom of gold, it has certain properties. You take 2 atoms of gold, the properties begin to change. Take 3 atoms of gold, and then step by step, you begin to see the evolution of the change of the material going. And for metals, it goes much faster because you don't need as many atoms for a metal particle.
Was it done with some chemical solutions, or
so this is a molecular beam. This molecular beam is in vacuum. So you have a source of your metal, let's say, you heat it up to a vapor, and you pass it through into a high vacuum chamber, in a hypersonic beam of some sort, right?
Mm.
And so as the vapor cools, it begins to aggregate, and then you start making little clusters, and then you can use essentially mass spectrometry to separate different size clusters from each other. They can use lasers or whatever to study then clusters that are all the same size, And then for the theorist, if you only have 3 or 4, at the time at least, if you have only 3 or 4 or 5, maybe less than 10 atoms together, you can actually do theory and do DFT calculations or whatever, and look what are the possible shapes for a cluster that has 9 atoms of gold. There are many possibilities, and then but some are more stable than others. And if you know the stable shape, then you can begin to calculate what the properties are. And then you find that there are some clusters are more stable than others, energetically more stable, or the shapes are more stable. So you get all this beautiful basic science at the metal cluster level. That was happening at the same time as the little particles of semiconductors were being born. In fact, the first conferences that I went to, like the Gordon Research Conferences or the other big conferences, they were all cluster conferences. There was a room full of hundreds of people working on gas phase, small clusters, with the, looking at the details of, this cluster with 4 atoms is shaped in a certain way, but, theory doesn't predict it this way. So what's missing in the theory? Really detailed analysis of these very small metal clusters. And here we are with these nanoparticles that now are nanometer size. They've got hundreds of atoms, completely other part of the size spectrum. And we're doing it in solution as opposed to the gas phase. It's dirty, they're ligands on it. It's like these people look at us like we're crazy. How can you understand anything in this dirty system, right?
Do you know Uwe Kreibich? He wrote this book by Kreibich and Vollmer on all of these clusters. And I saw one of his old cluster machines, and he was always advocating that you had to do it physically so you didn't have the ligands and so forth. Yeah, he spent his entire career on exactly what you're describing.
Right. And so it was a cultural, clash. The chemists clashing with the cluster physicists, right? That clash still goes on today in different areas, but chemists tend to make dirty things. And physicists don't like to study dirty things. They want to study things that are really pristine and well characterized.
Which can fit into their theories.
Which can feed into theory, yeah.
Yeah, we like spherical cows.